Assalamualaikum and very good morning to all. So I am Mohammed Rasli from Faculty of Mechanical Engineering. So my research title is One Factor at a Time Investigation or FAT investigation of injection molding process for thin wall laptop component via simulation. So this study aims to determine the optimal processing parameter for the injection molding process used to produce plastic products. So in this case of thin wall parts, such as laptop component, can be difficult to produce due to warpage and shrinkage defect. So the proper selection of parameters is essential to achieving high quality and functional parts. So in this study, we will use Moldflow simulation software to conduct one factor at a time or FAT investigation of mold temperature, fill time, fill pressure, and melt temperature to determine their effect on warpage and shrinkage. So this finding can be useful for improving the quality of thin wall plastic part and reducing manufacturing costs. So we go to introduction. As we know, thin wall manufacturing process has many obvious benefits, including reduced production costs, weight, shape, size variation, as well as accelerating the development of electronic products like mobile phones. So thin wall injection molding has benefits like faster cycle time and increased productivity, but it can lead to warpage and shrinkage issue. So warpage occurs due to an uneven cooling or residual stresses, and proper mold design and cooling techniques can reduce it. So shrinkage refers to reduction in size of plastic part after it cools and solidifies, and it can cause dimensional inaccuracy. So to minimize the shrinkage, manufacturers use a combination of process control and manufacturer selection. So here this simulation are a crucial aspect of injection molding, is to enable the manufacturer to predict how plastic parts will behave during the molding process. So by using the CIE software, injection molding simulation create a virtual model of the mold and simulate the injection molding process. So my study is on laptop bottom case. So if we can see here, this laptop bottom case is a large part and thin, so we call it thin wall part. So in this case, laptop casing is a crucial part of laptop structure, protecting internal component and providing structural support. So it's typically made of plastic using the thin wall injection molding process, which can produce complex shape with thin wall, reducing weight as well and maintaining the structural integrity. So the material used must be able to withstand high temperature generated by the laptop processor and meet aesthetic and functional requirements such as lightweight, durable, and easy to manufacture. So material selection and manufacturing process are critical to ensure the final product meets all the necessary specifications. So the methodology here is, we can see here in the flow chart. So first, a 3D model of the part to be molded is created using CAD software and or imported from existing file. The mold design is then created, which involves determining the number and location of injection point, designing the runner and gate system, and creating the mold cavity. So the 3D model of the part mold is the mesh, which involve dividing the model into a series of small elements of analysis. The simulation setup involve defining the process parameters such as mold temperature, melt temperature, injection pressure, and injection time. So this simulation is then run. The software calculates the flow of plastic material into the mold, cooling and the solidification of the part and other relevant process parameters. So based on the simulation result, the process parameter, mold design or material selection may be adjusted to optimize the process and improve the quality of the molded part. So for the first step is SolidWorks modeling. So as we can see here, the bottom case dimension as mentioned in this slide with the thickness of 1.5 millimeter. So the bottom case contains ribs that are 0.8 millimeter thick, and it was designed using SolidWorks software. So we can see here the part that we select here is a large part and very thin with 0.8 thickness. Okay, so the 3D modeling file was saved in IGS format to allow compatibility with Moldflow simulation software. Okay, so next we go to Moldflow. Okay, Moldflow here, for those who don't know, is mold design required software to create simulation setup, analyze mechanistic gate location and materials selection, molding window analysis, rapid fit analysis, and the effect of fit system and geometry on product manufacturing. So then mesh entities are generated, a mesh is created for analysis. So this is suggested to use the default global edge length. But if the mesh certificate fails to meet the specification requirement in Moldflow analysis, so the global edge length can be adjusted to a smaller or larger value than the default. So to start analysis, click on the mesh and begin the analysis. So the mesh statistic generated using mesh creation are presented to examine the aspect ratio and the corresponding statistical percentage. Ideally, the aspect ratio should be smaller. Okay, once the mesh process is completed, the gate location was selected. Okay, as we can see here, the recommended gate location for the bottom case, as suggested in the figure 3. You can see the arrow here, the yellow arrow. So the suggested location is deemed ideal for the gate position as it determines the surface finish, characteristic, and appearance of the window. So level of factor selection. So the Moldflow simulation is performed by utilizing 4 response parameters, and each factor has 5 levels that are incorporated into the process setting of the Moldflow software, where L3 will be the datum of this study. Okay, so this study will use the method which is known as OFAT, one factor at a time, which involves analyzing the impact of single factor on the response. So for example here in this table, we can see that, for example, if you want to study about the mold temperature factor, so we can vary the mold value, as you can see here, from 70 up to 90 with 5 levels. But the rest, the melt temperature, the injection pressure, injection time, we will keep that in constant for that case. For example, for the first run, for example here, we use the mold temperature of 70, and the rest factor is we will use the 260 degree for melt temperature, 95 megapascal for injection pressure, and 1 second for injection time. Okay, so this method enables to thorough investigation of the effect of a particular factor and helps determine if a change in output is due to the input level rather than a random error. Okay, for result and discussion, for factor A. Okay, mold temperature. So mold temperature is the temperature of the actual mold cavity and is considered one important factor that affect the quality of the product. Okay, so figure 4 at the bottom, at the upper here, shows the simulation result. Okay, so it's if so you can see here, as the mold temperature increase, the warpage of the part also increase. It shows that the cooling process during the molding plays a crucial role in the final shape and dimension of the part. So the mold designer should carefully consider the mold temperature setting and the cooling system design to ensure that the plastic part are produced in minimal warpage. So the graph at the bottom here shows that mold temperature has an effect on volumetric shrinkage, with higher temperature resulting in decreasing shrinkage. So this suggests that more temperature has the greatest impact on warpage and shrinkage, but it's necessary to determine the optimal value for controlling warpage and shrinkage through more temperature setting. And we go to factor B, melt temperature. So figure 6 illustrates the melt temperature against the warpage. So based on this graph, the trendline graph significantly decreases when the melt temperature increases. So there is a notable increase in warpage attributed to the low viscosity of the material at a high temperature, resulting in poor material freezing when the part is removed from the mold. So previous researcher mentioned that warpage increase as the melt temperature rise, and there is no melt temperature value that simultaneously minimize the warpage and melt temperature. So in figure 7, shows that the percentage value of volumetric shrinkage decreased gradually from 7.7% at 250 degree to 7.5% at 260 degree, and it increased again to 7.7% at 270 degree. So increasing the melt temperature can also lead to increased shrinkage. So other previous study have found that higher melt temperature lead to increased diametric shrinkage. So we go to factor C, injection pressure. So in figure 9, illustrate that graph injection pressure against the warpage. So the graph shows that increasing injection pressure lead to a drop in the value of warpage. So the most significant warpage value is observed at 85 megapascal. High injection pressure can reduce warpage on a part by helping the melted material fill the cavity space. So the location of the gate and the cooling channel design can be modified to reduce warpage. Excessive injection pressure can cause molecular orientation differences and residual stress leading to warpage. So in figure 10 shows how injection pressure affects shrinkage. So the graph reveals that as injection pressure increases, the shrinkage will be decreased. So by increasing injection pressure can reduce shrinkage due to better pressure transmission according to research. So meanwhile, increasing pressure inside the mold can decrease to local shrinkage. So for this case, top bottom case, by increasing injection pressure can reduce shrinkage, and the optimal injection pressure for thin wall product is 100 megapascal or higher. So for the injection time, so figure 11 shows the relationship between injection time and warpage. So the graph shows that gradually increasing pattern with increased injection time. Okay, the warpage of plastic is affected by the injection time in a certain way. As the injection time increase, the warpage of plastic gradually decrease. So the relationship between injection time and volumetric shrinkage also shown in figure 12. As injection time increase, the trend line rise and the percentage of shrinkage increase. So increasing injection time affects fill time, leading to short defects at 1.4 seconds, causing significant increase in deflection and shrinkage value. So therefore, the injection time setting parameter needs to be adjusted below 1.2 seconds to avoid short defect. So as a conclusion, this study has investigated the effect mold temperature, melt temperature, injection pressure, and injection time on warpage and shrinkage response. So the simulation results reveals that injection time parameter has significant impact on occurrence of warpage and shrinkage, as well as short defect. Okay, so the result shows that increasing mold temperature can increase warpage but reduce shrinkage, and at an optimal value of 75 degree or below can control greater warpage. So melt temperature should be set in the range of 255 to 260 degree to control warpage and prevent short defect. So higher injection pressure can reduce warpage but may cause longer freezing time on the z-axis, which can be addressed by changing gate location and cooling channel design. So increasing injection time can decrease warpage, but excessive injection time above 1.2 seconds may cause short defect. So in overall, this study offers important information on the optimal process parameter for injection molding of plastic laptop bottom case, which can lead to cost saving and better product quality. So that's all for me. Thank you.